This is Levitating Balloons Lab by Grace Kuza, Marie Camp, and Nick Hirschenberger. Introduction. So our main problem that we want to figure out is we have two balloons and we don't know the charges of either of them. We need to find out what charges they are. Our question is, how does the charge change when you charge the balloon for longer amounts of time? Our experimental design, we found the acceleration and from that the force of the two equally charged balloons, and we did this for 3 separate trials. Using that force that we calculated and Coulomb's law, we then found the charges of the balloons. For our main findings, as the amount of time the balloon was charged increased, the average electric force and the charge also increased. So for our experimental design, we blew up 2 balloons of equal mass, about 3.16 grams, and we charged each balloon by rubbing them against a sweater for a fixed amount of time. And this is done equally for each balloon. Trial 1, we charged them for 15 seconds, Trial 2 for 30, and Trial 3 for 45. We fixed one balloon onto a whiteboard using tape and fixed meter sticks on either side to act as a track for the second balloon that would not be fixed down. We then brought the other balloon right next to the fixed one and released it. We videotaped each trial and analyzed the acceleration on the tracker software, and then the acceleration was plugged into the F equals ma to determine force, and then using Coulomb's law to find the charges of the balloon for each trial. We assumed that each trial the balloon had equal charges, so we used the equation F equals k q squared over r squared. So this is just our experimental design in a model, but the green balloon is the fixed balloon, the white one is the free balloon. And then our system schema here, we have balloon 1 had electric force between that and balloon 2. And then balloon 1 also had contact force with the tape. We kept our whiteboard outside of the system schema, but we don't want to ignore friction. We're just keeping it outside of our schema for this scenario. Additionally, real quick, you can model this also on a computer with the orange being your fixed charge, your green being your free charge, and having them go away in a controlled environment where you can actually track the motion and the charge with less confounding variables. So real quick, some limitation and sources of error. The balloon didn't always stay in the track, so sometimes it wobbled or spun, which made tracker look at it differently. We also had to use a white balloon against a white background because some popped, so that might have skewed tracker's viewing ability a little bit. And possibly the unfixed balloon could have lost some charge due to contact with the whiteboard. So for scientific reasoning, we knew we needed either the electric potential energy or the electric force to solve for the charge, and we chose force. So we measured the mass of the balloons. We could measure the free balloon's acceleration using tracker, which we did, and measure the distance it traveled from the fixed balloon using tracker as well. And so we assumed the charges were equal in the same magnitude, so we called them q squared, and that's the only variable we need to solve for in this case. Both balloons were charged equally, and they should repel each other because like charges repel. So for our data and calculations, we use these 2 equations, Coulomb's law on the left for electric force, as well as force equals mass times acceleration on the right. And so from tracker, we measured the distance between the balloons, so that the free balloon, how far that traveled away from the fixed one. And we also used tracker to find the acceleration. We then multiplied each acceleration by the mass of the balloon, which is about 3.61 grams, and we found the net force at each point using the force equals ma. Then we took that known force and we used the equation for electric force on the left-hand side to solve for Q, which we can now assume is Q squared. And then we plugged in the net force as electric force, and the distance between the balloons was known as R, and the Ke was a known constant, so that left the only variable to solve was for Q squared, which would be the charge on our balloons. So as for our results, when we charged the balloon for 15 seconds, the charge in coulombs was about 1.5 times 10 to the negative 7 coulombs. Charging for 30 seconds, about 1.74 times 10 to the negative 7 coulombs. And then when we charged for 45 seconds, it jumped up a little bit to 3.24 times 10 to the negative 7 coulombs. On the left-hand side, we have a chart showing the number of electrons that were given off. And it's a lot lower for 15 and 30 seconds, but it jumped up pretty high after the 45-second mark, showing that more electrons were transferred. So as a conclusion, the average electric force as well as the charge of the balloon increased as the amount of time charging the balloon increased.